doing a hypothesis test. So far we've just looked at the basic mechanics, and we haven't looked too much at the logic behind it. Once we have the logic in hand, we can improve on that understanding, of course, but once we have that logic, we can then worry about interpreting our hypotheses instead of saying accept the null and have it in quotes still, or to reject the null. Remember, we accept, so-called accept the null hypothesis when we get into the acceptance region, the middle of the distribution, close to the hypothesized mean or proportion or whatever it is in the long run, and we'll reject the null when we get out of the acceptance region where the alpha is, and we call that the rejection region. Alright, we have this table here, 2x2 table. Across the top we will talk about what happens in reality. Now, we don't know what the reality or truth is, but we know that there are two possibilities. Either the null hypothesis, again, whatever it happens to be, is true, or the null hypothesis is false. It's one of those two, right? Of course, we must understand if the null is true, then the alternate, since it's the complement, must be false, and similarly, if the null is false, then the complement, the alternate, must be true. Alright, that's what's real, and we have no idea which of these two situations is real. True. Down this side here, we'll talk about the sample. Incomplete information, always. There are things in the real world that don't involve random samples, but still involve incomplete information. Court cases, medical tests, that type of thing. And as in court cases or medical tests or statistical tests, decisions are made. In the long run, we want those decisions to be made with appropriate wording and weights. Now we decide either, and we'll put quotes here again because we'll change this up once we've seen the logic. We either accept the null hypothesis when we get a sample value close to the hypothesized value, closeness being limited by the critical values that we calculate, or we reject the null. And so we say the sample value is too far from the hypothesized value, and when we reject the null, we turn around and accept the alternate. Okay, let's look at the first situation, and the first column first. Alright, this is where the null is true. So this value in the middle is the true mean or proportion or whatever it happens to be. So if that's a true one, and we get a sample value in the acceptance region, we will so-called accept the null. That's a correct decision. So put a check mark there. If the null is true, same scenario, and we get a sample value outside the acceptance region, somewhere out here in the tails, then we will reject the null. But we have that the null is true, so that's an error. This is called a type 1 error. The 1 is usually written as the Roman numeral 1, so type 1 error. The probability of making that type 1 error is the probability of getting out there in the tails, which we have set, and that probability is the alpha. Alright, we have half of alpha in the lower tail and half of the alpha in the upper tail, so together we have alpha in the tails, and that's the probability of getting out there. It's the probability of rejecting the null when the null is true. Alright, let's hang on for a second while I draw the other diagram. Alright, let's now assume that the null hypothesis is false. We'll look down the second column here. If the null hypothesis is false, this hypothesized distribution that we have up here that created the acceptance and rejection regions is now not true. And let's say that the second diagram here is the true distribution now. So, if the null is false, let's say this distribution is true, and we reject the null, that is, get out of the acceptance region, so down here or up here, alright, remember it's out where the alpha is, this portion, or over here. If we get there, we reject the null, and we do so correctly, and that's a correct decision. But if the null is false, alright, this distribution is in force, and we accept the null, that is, we get in the acceptance region, we've made a mistake, right? Instead of the true mean being here, it's here. Okay, so if the null is false and we accept it, that's an incorrect decision. That's called a type 2 error. Again, that's the Roman number 2. And the probability of making that type of error is given the label beta. So alpha is the probability of the first error, beta is the probability of the second error. Okay, so beta is actually this area here. It's the probability of getting in the acceptance region when the null is false. The only trouble is, in the real world, we don't know what the reality is, so we don't know where this true distribution is, and since we don't know where the true distribution is, we don't know what beta is. Beta, like any probability, is a number between 0 and 1, but in this case the maximum value that beta can have, so we'll say it's 1 minus alpha. It's sort of the maximum value is the area in the middle of the distribution. So statisticians have long understood that we have a problem here. We have two decisions. In each case we could make a true decision, correct decision, or we could make an error. No problem with the correct decisions. The problem happens to be with the errors. What can we do? Is there a way to decrease both errors? Yes, but that's not always available. The one way to do that is to increase the sample size. The only trouble is that we still don't know what beta will be. Okay? If we know what alpha is, we fix it. It's 5% or it's 1%. We can't fix it to 0%, but we can fix it to something small. When we do so, of course, beta can get large. Alright? Since the beta, maximum value of beta is 1 minus alpha. If alpha gets small, then the maximum value of beta becomes large. So that is not very pleasing. Alright, so of the two choices, the problem becomes with the acceptance of the null. We really, really don't want to make this error, which could be huge. Okay? It's like making a decision on sample data on a large investment, millions of dollars, and maybe you'll say, we'll accept this, and you can lose millions of dollars because you fell into this type 2 error. So in the long run, the way around this is to not accept the null, but say something weaker, and that is, do not reject the null. That's seems like, and it is, a very weak decision, but it avoids the problem of saying something too strong about the null. Okay, if we say something too strong about the null, we have the probability of making investment decisions or other decisions which could be an error. So from now on we'll say do not reject the null. The other side of the coin, if you like, where we reject the null, we understand the magnitude of that error probability. Alright, alpha, we can handle that. 5% or 1% or sometimes 10%, we can handle that. What we can't handle is beta. Okay? So from now on out we will say do not reject the null, because the null is possible. On the other hand, we will say reject the null. Okay, and that's all we can do with this table. In a little bit we'll try to show this logic, aspects of this logic with another story.